Imagine a high-speed internet that has never seen a server crash in 450 million years. It's running silently right beneath your boots at this second. We tend to look at forests as collections of individual trees, locked in a solitary battle for every inch of sunlight and drop of water. But that raises a massive question. How do organisms that cannot see, move, or hide survive a chaotic environment full of hungry pests, physical trauma, and unpredictable droughts? They survive because every tree you see is physically plugged into an active, calculating ecosystem that purposefully routes vital resources exactly where they are most needed. This subterranean architecture manages the survival of the forest through a decentralized system of logistics that operates without a central hub. To understand how this works, we have to look underground. The soil is densely packed with trillions of microscopic fungal threads, sprawling outward in every direction. This diagram shows roots connecting to blowing thread-like vector lines called hyphae. These microscopic filaments act like organic fiber optics, linking the forest. Watch the continuous two-way flow. It's a massive logistics hub. Trees pump carbon down, and the network pushes mineral goods back up. The fungi acquire those goods by actively mining phosphorus and nitrogen directly from the earth, fueling a relentless subterranean economy. This biological hardware transforms individual, stationary trees into a unified, interdependent market. This same infrastructure also functions as a data network, transmitting information across the forest floor. This top-down map illustrates a tree attacked by insects. The victim tree flashes a chemical warning signal that propagates instantly along the mycelial filaments. Surrounding nodes receive this signal and expand their perimeters, representing neighboring trees preemptively boosting immune defenses before pests arrive. The fungi act as active data translators. They take the specific chemical language of an infested oak tree and convert it into an actionable defense signal that a nearby pine can immediately understand. The architecture of this system also provides incredible resilience, especially when we look at the relationship between the oldest trees and the newest growth. Elder trees use the network to identify struggling saplings trapped in the dark understory. Once located, the older trees systematically pump sugar through the fungal conduits to keep those younger trees alive. If a hiker's boot severs a vital connection, the system doesn't crash. As the schematic shows, when a break occurs, the flow instantly diverts along alternative outward branches to reach the exact same destination. The network functions without a single point of failure, autonomously rerouting resources to maintain the forest's stability, regardless of physical disruption. When you are sweeping over this dense canopy, you are actually looking at a single, unified, living organism. A forest is an intelligent supercomputer, constantly executing complex algorithms to balance its resources. Unlike human data centers that consume massive amounts of electricity, this biological internet operates entirely in the negative. It computes the survival of the ecosystem while simultaneously pulling massive quantities of carbon dioxide from the atmosphere and locking it safely into the soil. Human engineering is finally taking some notes. Bioengineers are actively copying these adaptive fungal algorithms to design our next generation of infrastructure. Instead of manufacturing raw materials, we are moving toward a reality where we literally grow our technology, using mycelium-like scaffolds to form our architecture. By applying fungal network logic, developers are already testing biodegradable computers and designing self-healing buildings that can repair their own structural microfractures. The forest standing outside your door is the most sophisticated network on Earth. It is an ancient calculating system, and humanity is finally learning how to plug in.